Good afternoon. I hope the final went well. Sorry I couldn't be there for you, but I hope you did pretty well anyway. Today we're going to be starting Chapter 4, and before we actually do that, Chapter 4 is all about exponential functions and then logarithmic functions, which kind of go right along with those. Before we do that, we're going to take a quick little pause to review exponents and square roots from Algebra 2. So our big things here today, just remembering what is an exponent, this big one here, what are the rules for working with exponents. That's going to be a big one because without having an understanding of those rules, we really can't apply them in any way. And then what does a negative or fractional exponent mean? That's going to be a big one too because we're not always going to have whole number exponents. What does it mean to take something to the 4.5 power or something like that? And so we'll discuss that a little bit too. Everything in this section here is review from last year. But if there's anything that we're not understanding, make sure we're stopping and getting a better understanding of that before we move on. So, to start off with, let's just quickly review what an exponent is. And so at the basic level here, integer exponents are all about repeated multiplication. So when you see something like 4 to the 5th, we have here, or rather 5 to the 4th, what that means is just to take that base, the 5 is the base, and multiply by itself 1, 2, 3, 4 times. Now that's something that calculators are obviously really good at. I'm not really sure off the top of my head what 5 to the 4th actually is, but we could look that up for sure. But we just take 5 times 5 times 5 times 5, and ends up being 625. And so calculating these with the help of a calculator, not too bad. Or you can get things like a multiplication chart that'll help out a lot too. We'll sometimes see those. Now, with things like fractions raised to a power, it's the same thing. Something like 1/6 to the 6th power just means to take 1/6 times 1/6 times 1/6 times 1/6 times 1/6 times 1/6. And if you remember how we multiply fractions, this is just a matter of multiplying across the top and then multiplying right across the bottom. And so what this turns into is that 1/6 to the 6th actually turns into 1 to the 6th over 6 to the 6th. It actually makes it pretty easy to calculate. 1 to the 6th is just 1. 6 to the 6th, again, I need a calculator for that one, but for 46,656. So 1 over 46,656. That's a whole lot easier than actually trying to multiply 1/6 times itself a whole bunch of times in a calculator. So that one rule there can help you out a lot. Now, we extended that idea last year into negative exponents. And if we kind of think about following the pattern, 2 to the 4th just means to take 2 times 2 times 2 times 2. Same with 2 to the 3rd. Same with 2 squared. 2 to the 1st is just 2. And if we kind of follow this pattern, go ahead and do this real quick. 2 to the 4th is 16. 2 to the 3rd is 8. 2 squared is 4. 2 to the 1st is 2. As we're going down here each time, because we're just decreasing the power of 2, we're dividing by 2 each time. And if we follow this pattern and we keep going, 2 to the 0th power, by definition, has to be just 1. Because we're just dividing by 2 each time to go down. And in that case, everything to the 0 power would follow that exact same pattern. Anything to the 0 power is 1. Now, when we get into these negative exponents, keep following the pattern. We're going to divide by 2 again. And so 1 divided by 2 is just 1/2. Keep going. Dividing by 2 again. 2 to the negative 2 power is 1 over 4, or 1 over 2 squared. And so what happens here is any negative exponent actually turns into the reciprocal. If we have if we have 5 to the negative 3rd power, that's the same as 1 over 5 to the positive 3rd power. It's just that reciprocal relationship going on there. So here's a list of exponent rules. You can certainly pause this video at any point, write these down. These are things that you need to know. These are things that you've worked with before. You've explored why these work before. Now it's just time that we have to know these rules. So our product rule, taking a base times a base. When the bases are the same, we add the powers. And so you might see something like 3 squared times 3 to the 5th equals 3 to the 7th, because 2 plus 5 is 7. This works no matter what the base is, as long as they're the same. In the same idea here, if we're dividing bases, we're going to subtract the powers. I'll do an example of that and kind of show you real quick what I think about when I do these. But if multiplying is addition, of course division is subtraction. Next, we've got our power of a power rule. And this one says that if we raise an exponential expression to another exponential expression, the powers get multiplied. So 3 squared all raised to the 5th is 3 to the 10th. Then we've got kind of what you'd consider almost your distributive property. Now be careful with this. This is not the distributive property. It's a similar idea, but it's not the same thing. If we have a multiplication problem raised to the nth power, raised to a power, that power can apply to both things. It has to be either multiplication or, as you see down below here, division. If there's an addition in there, it does not work. This is not the distributive property. So be very careful with that. So I just want to go ahead and just kind of show you one thing about these. These first couple are probably the big ones. The way I think about it, especially the second one here, is if I end up with something like, I don't know, x to the 3rd on top and x to the 6th on the bottom, remember what these actually mean. This means that it's x times x times x on the top over x, 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 x. So it's 5, 6 on the bottom. And so if we remember our canceling rules here, because there's a common factor of x there, and there, and there, that all cancels out. Well, there's nothing left on the top. That doesn't mean there's really nothing. That means there's a 1. And then 3x's on the bottom, or x to the 3rd. And as you'll notice here, 3 minus 6 would be negative 3, so we end up with a positive 3 in the denominator. I like to think of it more like this canceling out rule. So when I see this x to the 3rd over x to the 6th, I just think of, okay, if I take away 3 there, there'll be 0 left. If I take away 3 there, there'll be 3 left. So x to the 0 is 1, x to the 3rd on the bottom. That's what I'm thinking about, but the rule specifically is subtract the top by the bottom, and that's what you get. So let's take a look at some examples here. First of all, we got x to the 4th times x to the 7th. The rule there is pretty simple. We just add, so we get x to the 11th power. Next one here, y to the 4th times y to the negative 7th. Again, applying our rule, that's just going to be y to the negative 3rd, but we never leave negative exponents in problems, so this is going to be 1 over y to the positive 3rd. We always want to write it in this notation with the positive exponent. Here we got c to the 9th over c to the 5th. Again, our rule is subtraction, so 9 minus 5 is 4. This is going to be c to the 4th. I think about it personally as I have 5 in the bottom, so I take away all 5. I have 5 in the bottom, so I take away 5, and I have 4 left. So that is c to the 4th. But if you use your rule, c to the 9th minus the 5th is c to the 4th power, if you like the rule better. Next one down, this is our power of a power, b to the 4th raised to the 5th power. Just as a quick side note here, that would mean that I'm taking, b to the 4th times 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 b to the 4th. And according to our very first rule, way up here, that just means we add. And 4 plus 4 plus 4 plus 4 plus 4, well, that's 20. Now, a shorter way, of course, 4 times 5 is 20. So that's why we have that power of a power rule being to multiply. So let me just go ahead and get rid of all of that. Now that we have that rule to work with, our power of a power says we take b to the 4th times the 5th, which is b to the 20th. Next one down, we've got 3x raised to the 3rd power. So that just means it's almost like the distributive property, but it's not quite. We're going to raise 3 to the 3rd power, which is 27. And we're going to raise x to the 3rd power, which is x to the 3rd. Everything in those parentheses gets raised to the 3rd power. And our final example here, same deal. This one's with division, just everything getting raised to the 5th power, x to the 5th over 2 to the 5th, which if we care enough to simplify that, I believe is 32. So x to the 5th over 32. So we are going to, of course, have examples where we need to combine those ideas. And so it's always just a matter of following your order of operations as much as possible. In kind of the, as far as we can go with the exponents and the variables still in there. So the first thing I'm seeing here is this 3 on the outside. That would need to get applied to everything on the inside. So I'd have 2a to the 3rd b squared from this first one times, well, 3 times 3 is 20, or 3 to the 3rd is 27, a to the 3rd b to the 12th because of our multiplication rule there. Now this is all multiplication. There's actually no reason at all to have these parentheses in there anymore. So I can just go ahead and start multiplying everything through. And to do that, 27 times 2 is 54. We've got a to the 3rd, well that makes a to the 6th, because 3 plus 3 is 6. And I've got b to the 2 plus b to the 12 is b to the 14th. Again, we're multiplying everything. There's no need to distribute anything. There's no plus signs here. Just multiply your terms together. Same thing here with b. We're going to go in, and the first thing I'm going to do is just apply this exponent to everything. X to the third over y to the third times, well, now we're going to have y to the 8th, x to the 4th over z to the 4th. Now, we can take as many steps as we want here, and it's probably not a bad idea to just slow down and let's combine everything across first, deal with the top of our fraction first, then we'll deal with the bottom of our fraction. So on the top, I've got x to the third times x to the 4th. Well, that's going to make x to the 7th, and I've got a y to the 8th. On the bottom, I've just got y to the 3rd, z to the 4th. Now the last thing here is the y's. I have 8 on top, 3 on the bottom. Our rule is subtract. 8 minus 3 is 5. And so I have x to the 7th, y to the 5th, over z to the 4th power. That's honestly about as much as we're really going to need to know with these exponent rules. Now, the last part of this is we've got some negatives in here. You won't see a ton of super complicated things with negatives, but again, the same kind of rules apply. I would deal with these negatives first. Just go ahead and move everything around. This t to the 4th, or t to the negative 4th would move down. This s to the negative 2nd would move up. So the s up there already, and then another s squared from that one moving up. There's a 2 at the bottom, a t squared, and then a t to the 4th from this one moving down. Then I go ahead and combine. 6s to the 3rd over 2t to the 6th. And then the last thing, well, 6 over 2 is just 3. So 3s to the 3rd over t to the 6th. Something like b, what I would do first is, just because there's that negative sign, I'd go ahead and flip the whole thing over. 3z to the 3rd over y, all raised to the 2nd power. That negative exponent, again, is just the reciprocal, flipping the top and the bottom. Now it works just like everything we've done before. Okay, the last part of this is going to be our rational exponents. Or rational exponents are just square roots. And so again, this is a really important thing that you should definitely have written down. If you see a rational exponent, it can be written either way. A to the m over n is the nth root of a raised to the m power, or a to the m power and then take the nth root. The order actually doesn't matter at all. And so use it to your advantage. Whichever way is easier, use it. So just a couple of examples here. 4 to the 1/2. Well, since the 2 is in the bottom, that's the root. So this is the square root of 4 to the 1st power, which I don't need to write. Square root of 4 is 2. Similar thing here. 8 to the 2/3. Well, the 3 is in the bottom, so that's the 3rd root of 8 squared, or the 3rd root of 8 raised to the 2nd power. Now in this case, the second one is easier because the 3rd root of 8 is 2, and then 2 squared is 4. Or if I did it this way, I'd have to somehow figure out the cube root of 64, and I don't want to do that. Last thing here, we've got this negative sign. That's just going to flip the whole thing over, and so we've got 1 over the cube root of 125 to the 1st power. Sorry, I covered that up, which is 1/5. And we'll throw some variables in there as our last example here. So we've got, again, a 3 in the top, which means this is all raised to the 3rd power. And then the square root. Doesn't really matter which order we do it in, but sometimes it does save you a little bit of trouble one way or the other. This way it doesn't really matter much. So we've got the square root of 2a to the 3rd, b to the 4th, all raised to the 3rd power. I'm going to do the 3rd power first, I think. So this is going to give me the square root. 2 to the 3rd is 8. A to the 3rd is a to the 9th. And b to the 4th to the 3rd is b to the 12th. Now what I'm going to do is go through and look for perfect squares that go into all of these. Now 8 isn't a perfect square, but 4 is, and it goes in. So I'd have the square root of 4 times the square root of 2. I'm going to drop the 2 because it's just a square root. Now a to the 9th is not a perfect square, but a to the 8th is. The square root of a to the 8th would just be a to the 4th. And then I have another square root of a just chilling out. B to the 12th is a perfect square, and so I can leave it like that, which finally lets me just go ahead and take the square roots of the things I know. So I'd have 2, a to the 4th, b to the 12th,